Hello and salam sejahtera. My name is Patricia JELAWAI David. My matrix number B0820103889 and I'm from 1 BEI section 1/2 and today for this video we will learn about magnetism. We will explain what is magnetism, how it works, the example of magnetism, and the types. We also gonna explain about bar magnet, magnetic fields, what is magnetic fields, there is examples of all of this, and without any further ado, let's get to the video.
Hi, today we will learn about magnetism. First, we will need to know what is magnetism. Magnetism is one of the aspects of the fundamental electromagnetic force. There are four types of magnetism. First, paramagnetism. Second, dimagnetism. Third, electromagnetism. And fourth, ferromagnetism. This is explanation for each type of magnetism. First, paramagnetism describes certain materials that may be weakly attracted to magnet, but that do not retain a permanent magnetic field themselves. Second, dimagnetism is a property exhibited by all materials, but which is typically most obvious in materials we think of as non-magnetic. Third, electromagnetism occurs when the electric current is passed through the wire. And fourth, materials that are strongly attracted to magnets are called ferromagnetic. Ferromagnetic materials include lodestone, iron, nickel, cobalt, and various rare earth materials including neodymium. Next, what is magnetic field?
A magnetic field is the area around the magnetic field where the poles experience the force of attraction and repulsion. Fun fact, did you know our own very Earth is a giant magnet? The Earth is surrounded by a system of magnetic field called the magnetosphere. In fact, this is how compasses work, determining which direction we are relatively to the poles, which is either north or south. So we know that a magnet always has two poles. It has a north pole and a south pole. And next, I'll be explaining about magnetic properties. As we know, there are north and south pole. It works in a simple premise that the same polarity is repulsive towards each other, while opposite polarity attract to each other. It has a magnetic dipoles where we have positive charge and a negative charge. Remember that field line would come out of it and negative charge would all come into it. But if we move them next to each other, we will have the pattern of electric dipole. The electric field lines are identical to those of magnetic field lines. But magnetic monopole does not exist in magnetism or in general science. If either north pole exists, there are also going to be south pole. Alright, now I'm using a paid page to simulate Faraday's law of electromagnetic induction and how it works generally. But first thing first, I'm going to explain about magnetic flux. Magnetic flux is a measurement of the total magnetic field which passes through a given area, which in this case, this copper wire, which has roughly 4 turns of coil. So let me open up the field lines. A flux is depicted as lines in a plane which contains or intersect electric charge poles or magnetic poles. We have like 1, 2, 3 and 4 field lines going through this area right here. So it is telling us what the flux is. So now back to Faraday's law. So what is Faraday's law of electromagnetic induction? Faraday's law states that a voltage will be induced in coil when the magnetic flux through the coil changes over time. Well, I will demonstrate here. If I move the magnet to the copper coil, you can see that I'm changing the flux. When I change the flux, I induce a voltage here in the voltmeter, which then induce current and light up the bulb here. And you will notice that if the magnet were to move slowly to the copper coil, I don't get a lot of voltage. Where if I go fast, I will get a much bigger voltage through the deflection of the voltmeter here. So that means the rate of change of the rate of change of flux is going to influence the voltage, in turn to determine the current. But if I just put the magnet here right into the copper coil, where I don't move it, I don't get a change of flux, and when I don't get a change of flux, I don't induce a voltage, and I also don't have a current. So to put this in a perspective, to get electric energy, we have to put in energy, in this case kinetic energy, to the movement of the magnet. And I will also demonstrate how a lower amount of turns of copper influence the voltage. So even if I move this magnet to the copper turn faster than normal, I still don't get a big deflection on the voltmeter. So we can conclude that a turn of copper coil influence the voltage. From what I have explained, Faraday's law can induce voltage and current from the simulation I have shown earlier. Through a base conclusion, the Faraday's law is a basic law of electromagnetism, where we know a magnet can induce voltage and current where its magnetic field interact with an electric circuit to produce electromotive force, which is an EMF, where a phenomenon also known as electromagnetic induction through moving a magnet toward or away from the coil, moving the coil into or out of the magnetic field, and rotating the coil relative to the magnet or vice versa. Faraday's law has benefited us immensely throughout this modern age. We can see the application from the hydroelectric dam we as a humankind has created today, where the hydro dam uses a rotating magnet around a coil to induce electricity and in turn power our civilization. The same principle also shown for other type of renewable energy, such as wind turbine, where it is commonly used in western part of the world as the wind speed there is higher and much more consistent. And thus, I'm FRANKLYN UMUT Anak LIMBAN, Session 1/2 BEEI, metric number B0820100175, is signing off.